This video will cover molecular shapes and hybridization. The three-dimensional shape of molecules is important to understanding their chemistry, and their three-dimensional shape is predicted by something called Vesper Theory. Vesper stands for Valence Shell Electron Pair Repulsion Theory. And basically what this means is that electron pairs, which are negatively charged, repel one another, and they want to be as far apart as possible. So, for example, if an atom has two electron pairs, the farthest apart that they can be in space is 180 degrees from one another. If an atom has three electron pairs, the furthest apart they can be is 120 degrees. And if an atom has four electron pairs around it, which is the maximum that we'll see in this class, the farthest apart that they can be is 109.5 degrees. And so Vesper Theory states that depending on the number of electron pairs that we're trying to position around an atom, they're going to adopt these different geometries based on how many electron pairs we're trying to space apart. And remember that these electron pairs are going to be held in orbitals. And if you remember from general chemistry, there's two types of orbitals we're talking about, at least in the first two rows of the periodic table, and those are s and p orbitals. Remember that the s orbital is spherical, and the p orbitals each have two lobes, and they're spaced apart at 90-degree angles from one another. And so neither one of these types of orbitals is going to allow us to get these angles that Vesper Theory states that we should have in these different molecules. So the way that we account for this is by using something called hybrid orbitals. Hybrid orbitals are mixtures of the atomic orbitals s and p. So for example, we can mix one s orbital and one p orbital together to get an sp orbital. If we mix together an s and two p orbitals, we get an SP2 orbital. And if we mix together all four of these orbitals, an s plus 3p orbitals, we get something called an SP3 orbital. These are called hybrid orbitals. An sp orbital is 50% s and 50% p. An sp2 orbital is 33% s and 66% p. An sp3 orbital is 25% s and 75% p. Next, we'll talk about what do these hybrid orbitals look like. We'll start with sp hybrid orbitals. Sp hybrid orbitals are a combination of one s and one p orbital, and they look like this. We have two sp orbitals because whenever we hybridize orbitals, we end up with the same number of orbitals we started with. So one s and one p gives us two sp orbitals. And remember that if we put two electron pairs as far apart as we can in space, they're going to be 180 degrees from one another. And that gives us something called linear geometry. And the geometry will make more sense in a moment when we look at a molecule that uses sp hybrid orbitals. So an example of a molecule that uses sp hybrid orbitals is beryllium hydride. So what we're going to do is we're going to draw the orbitals involved in the bonding of this molecule. We're going to label the hybridization and predict the bond angles. First, we'll start by drawing a Lewis structure. This Lewis structure should have four valence electrons. Two come from beryllium, which is in the second column, and one each for each hydrogen, giving us a total of four valence electrons. We'll choose as our central atom the atom that can make the most bonds, which in this case is going to be beryllium. And we have four valence electrons or two bonds, so we can make each of two bonds to hydrogen. So this is our Lewis structure for beryllium hydride. So we have two electron pairs on beryllium. Vesper theory tells us that two groups are going to want to be 180 degrees apart. And for two groups, we will need two hybrid orbitals, which means that we will hybridize an s and a p atomic orbital to give us an sp hybrid orbital. So our hybridization on the beryllium will be sp. The bond angles will be 180 degrees. And now we'll draw the orbitals, and what that's going to look like is a central beryllium atom, which is going to be using those two sp hybrid orbitals. And it's going to be bonding to a hydrogen. The hydrogen is going to be using its s orbital. It only has 2 electrons, therefore it only needs 1 orbital. It's going to use the lowest energy, which is going to be that s orbital. So if we draw that bonding picture of the orbitals, what we're going to have is 2 s orbitals on the hydrogens, 2 sp hybridized orbitals on the beryllium, giving us a bond angle of 180 degrees. There are 2 sigma bonds here. And this is what our molecule of beryllium hydride is going to look like. Next, we'll look at a molecule that uses SP2 hybridized orbitals. SP2 hybrid orbitals are a combination of 1s and 2p orbitals. So if we combine 3 atomic orbitals, we'll end up with 3 hybrid orbitals, 3 SP2 orbitals. The farthest apart we can get 3 things in space, according to Vesper, is going to be 120 degrees. And this is called trigonal planar geometry. An example of a molecule that uses SP2 hybrid orbitals and has trigonal planar geometry is borane, or BH3. Again, we'll start with a Lewis structure. Boron is going to come with 3 electrons because it's in the third group. Hydrogen, there are 3 of them, and each of them come with 1 electron. That gives us 6 electrons total. So if we draw our Lewis structure, we'll put the atom in the middle capable of forming the most bonds. That's going to be boron. Draw 3 bonds to each of the hydrogens. That uses all 6 of our electrons. This is our complete Lewis structure. We have 3 groups on boron. That's going to give us 120 degree bond angles, and that's going to mean that we need 3 hybrid orbitals. So we'll have SP2 hybrid orbitals. So if we draw a picture of the bonding in this molecule, again we'll have boron in the middle. That boron will have 3 SP2 hybridized orbitals. And again, the hydrogens each only have 1 electron pair to contend with, so they will just be using their s orbitals. The farthest apart in space, we can get these 3 hybrid orbitals containing these 3 pairs of electrons is 120 degrees. We have 3 sigma bonds here, 1 there, 1 there, and 1 there. And remember that the geometry for this is trigonal planar. What that means is 3 things in a plane, evenly spaced. So all of the atoms in this molecule are in the same plane. Finally, we'll look at SP3 hybrids. SP3 hybrid orbitals are a combination of 1s and 3p atomic orbitals, and so we're going to end up with 4 SP3 hybrid orbitals. This is what our 4 SP3 hybrid orbitals look like. You can think of this one and this one in the plane of the page. This one is coming out towards us, and this one is going back away from us. And Vesper theory states that if we have 4 electron pairs, the farthest apart we can get them in space is going to be 109.5 degrees apart. And therefore those 4 SP3 orbitals are going to have what's called tetrahedral geometry. Our example molecule for SP3 hybridization is going to be methane, or CH4. Again, we'll start with a Lewis structure. Carbon comes with 4 valence electrons, hydrogen has 1, and we have 4 hydrogens, so that's a total of 8 valence electrons. We'll put the atom in the middle that can form the most bonds, that's going to be carbon. 4 single bonds to hydrogen, that uses our 8 valence electrons. This is our Lewis structure for methane. If we have 4 groups, they're going to be 109 degrees apart, 109.5 degrees apart, and they're going to use SP3 hybrid orbitals. And what this molecule is going to look like in 3-dimensional space is, again, we're going to start with that carbon atom in the middle. It's going to have the 4 SP3 hybridized orbitals, 2 in the plane of the paper, 1 going back into the plane of the paper, 1 coming out at us out of the plane of the paper. These are all going to be the SP3 orbitals. There are 4 of them. Again, hydrogen is just going to use its s orbital to hold its 1 pair of electrons. Each of these bonds is going to be spaced apart from each other bond by 109.5 degrees. We have 4 sigma bonds here between the s orbital of hydrogen and the SP3 hybridized orbital of carbon, and this is what our molecule of methane is going to look like. Now, this tetrahedral geometry is the first geometry we're looking at where all of the atoms are not in the plane of the page, and there are a lot of organic molecules that require 3D interpretations, and so we've come up with ways to express these 3-dimensional nature in our 2-dimensional drawings. And we call this drawing with perspective. We're drawing on a flat page what something looks like in 3 dimensions. And so if we draw methane with perspective, we're going to have that carbon atom in the plane of the page. And we're going to show our bonds. 2 of our bonds can be in the plane of the page to 2 of our hydrogens. But if we draw all 3 of these atoms in the plane of the page, one of the remaining bonds of hydrogen will be coming out towards us, and one will be going back into the paper away from us. We show the bond coming towards us as a wedge. So that's the bond that's coming out of the page towards us. The bond that's going away from us is shown in dashes. And this is how we indicate that this molecule is actually 3-dimensional, even though we have to draw it flat. And so this is something you'll want to practice because we'll be using this quite a bit later in the semester. So up until this point, the molecules we've looked at have not contained multiple bonds or lone pairs, but Vesper theory can apply to these types of molecules as well. So now we'll look at Vesper for a molecule that contains lone pairs. And our example that we'll look at here will be a molecule of water. So again, we'll start with our Lewis structure. Lewis structure of water looks like this. It has 2 bonds to hydrogen and 2 lone pairs. Remember that Vesper applies to lone pairs of electrons, or it applies to pairs of electrons and getting those pairs of electrons as far apart as possible. In this case, we have 4 pairs of electrons, 2 lone pairs, and 2 bonds that we're trying to get as far apart as possible. The farthest apart in space that we can get 4 electron pairs is 109.5 degrees, which is going to mean that we need SP3 hybridized orbitals. And so when we draw this molecule, what this is going to look like, we're going to have that central oxygen atom. It's going to have SP3 hybridization, so it's going to have 4 SP3 hybrid orbitals around it. two of those SP3 hybridized orbitals are going to form the bonds with the s orbitals of the hydrogen. Does not matter which two you choose. And the other two hybridized orbitals are going to contain lone pairs. And so this is what our molecule of water is going to look like when we draw out its orbitals. What about molecules with multiple bonds? When we're looking at a molecule with multiple bonds, the first bond of a multiple bond is going to be a sigma bond, and it's going to occupy a hybrid orbital. The second bond is going to involve an unhybridized orbital. It's going to specifically involve an unhybridized p orbital because it's a pi bond, and pi bonds involve p orbitals, overlap of p orbitals. If the multiple bond is a triple bond, then that third bond is also going to be a pi bond. It's going to involve an unhybridized p orbital that will be perpendicular to the first pi bond, to the first p orbital. So for example, let's look at a molecule of ethene. First, like always, we're going to start with a Lewis structure. And the Lewis structure of ethene is going to look like this. It contains a double bond. If you're not sure how I got that Lewis structure, pause the video and try that on your own. The hydrogen atoms, again, only have one electron pair, so they're going to be using their s orbitals. It's the carbons that are going to require hybridization to accommodate all of the electron pairs around them. And each carbon has three groups around it, 3 sigma bonds. The farthest apart in space that we can get 3 pairs of electrons is going to be 120 degrees, and this is going to require SP2 hybridization for each of those carbons. Remember that we're only accommodating 3 groups with hybrid orbitals because the second bond of that multiple bond, of that double bond, is going to be accommodated in an unhybridized p orbital because it's a pi bond. And so drawing this out, the orbital picture of ethene out, is a little complicated because now we're talking about both sigma and pi bonds. So what I'm going to do is try to draw that for you. So again, we'll have 2 carbons. These are our central atoms, and each of those carbons is going to have 3 SP2 hybridized orbitals around it. There's 1 for each of them, 2, and 3. Alright, and all of those are in a plane perpendicular to the paper. And so this hybrid orbital are going into and out of the paper respectively, as are this one and this one. Alright, now we're going to draw in our sigma bonds. So we have a sigma bond to a hydrogen over here, and here, and here, and here. And then finally we need the unhybridized p orbitals on each of these carbons that are going to allow us to form that pi bond. That's responsible for the double bond in ethene. Alright, so this is a pi bond. And we also have 4 sigma bonds here. There's 1, 2, 3, 4 between the carbon and the hydrogens, and a final sigma bond that makes up the first bond of that double bond. Alright, and these p orbitals are perpendicular to the plane of the sp orbitals of the carbon. What about ethine? Ethine is going to have a triple bond between 2 carbons, and if you draw out that Lewis structure, it's going to look like this. Again, if you're not sure how I got that, pause this and try that on your own. Here we're trying to space 2 groups about each of those carbons. The farthest apart that we can get 2 groups is going to be 180 degrees. This is going to require sp orbitals. And the second and third bonds of this triple bond here are going to come from pi bonds that involve unhybridized p orbitals. And so I'm not going to draw this one out. I want you to try that on your own. It is a little difficult, so what you might want to do is draw the pi bond network, the p orbitals, on a separate picture from the hybridized orbitals that are involved in the sigma bonds. So try that on your own, and we will talk more about that in class.